It's amazing to be here. First off, thanks to Xanadu for hosting the event and having me here. It's great to be in Toronto. I'm going to tell you about our efforts at Waterloo to launch an open source quantum computer. But before I do, perfect timing, Matt. I just want to also acknowledge all the great people that make this hackathon work. And as we look back in time at the size of the prizes, what year was this, you guys?
2019.
2019. I hope you recognize a few of these people. 3 out of the 4 of these winners, day trippers, are in the room today. What did you guys do with that $250? That's what I really want to know. I'm taking it off your stipend. No, just kidding. It's fun to be part of this community. It's QHack's a great event. Great to see you guys getting older. It's not just me. As you can guess, maybe as you can guess, I'm a professor at the University of Waterloo, and you're all my children, but specifically, there's a significant amount of this audience who was at one point my graduate students or undergraduates, so it's really rewarding for me personally to see everything that you guys go out and do in the world. And I could talk about science all day and all the great things that we've all done at the University of Waterloo, but I want to focus on this group of people. I've replaced my picture with my amazing Photoshop skills, with the picture of us sort of launching this open quantum design foundation in the basement of the IQC building right beside Rajabul Islam's ion traps, and I'll show you more pictures, but this is a group of theorists and experimentalists who I'm going to introduce quite a few of them around that table. But at the end of the table, it's hard to see are Crystal Sanko and Rajabul Islam, who are my colleagues at the Institute for Quantum Computing, who are building several ion trap quantum computers. Okay, so these have been under development at the University of Waterloo since about 2017. We've sunk about $10 million into these machines. And so what open quantum design is, and I'm going to tell you all about it over the next hour, is essentially our effort in launching out this quantum computer stack and out there for the whole world to enjoy. So let's see, anyone in the room here? Roger, I think you're on the laptop there. Sorry, I didn't get you in person in the room, but a great group of people. I wanted to start by asking you guys, you're out there in the trenches every day, building quantum computers. What's the hardest part of building a quantum computer? Writ large. Anyone want to throw something at me? Cash, is that what that is? Cold hard cash?
Isn't the cooling one of the hardest parts?
Maybe. Good answer. What else? What's so hard about it?
Creating the platform or whatever is going to become your qubit and having many of them.
Having many of them, right, that's right. There's many different qubit, I would guess I would call them candidate substrates or something like that, right? Which are the ones that are going to win? What does winning even mean, right? Other answers? I'm just stalling here because I don't have enough slides, so.
Well, error rates.
Error rates, getting them down?
Threshold, yeah.
Yeah, you get them down so that you can basically error correct, right? Beyond or underneath the threshold.
I think for places that aren't like right next to a quantum hardware provider, just getting your hands on hardware, like the right kind of hardware, fabrication facilities, etc., can be difficult.
I love that answer. I'm going to address that multiple times here. Right here, what's so hard about quantum computing? Come on, seriously.
I think it's really hard to come up with a scalable two-dimensional circuit topology.
Oh my God, I love it. I'm just going to stop there because I heard that word, scaling. And I think every answer here had something to do with scaling, either economically, I mean seriously, or physically. But we've seen this a million times. This is Moore's law. And we're used to the statement of Moore's law, what it is. Transistor count doubling every X, whatever, It's really an economic statement. It's a statement about how, investment has gone into, fab facilities, which essentially semiconductor fabs still take an investment of over $100 billion a year annually, globally. So there's a huge amount of investment in the scaling of conventional hardware. And we, arguably haven't yet triggered, or we're just on the kind of bottom of this cusp of triggering the scaling that we require to build the quantum computing hardware that we want to build, right? So all of your answers, I think, feed into this sort of larger narrative of that. How do we scale up our efforts? And it's, particularly, I guess, relevant for us in academia who are used to working on things like, which qubit is the best one? What's the best bet at the lower levels? How do we build out these control stacks and so on? But it's very rare that we think about how we scale, the ecosystem and the economy around quantum computing. And in some sense, what we're trying to do with ideas like quantum advantage, of course, is to beat calculations or beat simulations or whatever you want to call it that happen in silicon computers, right? So we somehow have to match this scaling or beat it in some sense. So I mentioned academia, which is where I spend most of my time. But there's other organizational structures, let me put it that way, that help us build quantum computers. And so academia has a role, but it's typically not to scale, right? Academics don't bring, an academic group doesn't bring in a $100 million Series A. They don't even know what that means, right? But we, in academia, typically prototype, explore to research and development, and all those types of things. So in today's world, the question of scaling falls largely to, I left it off, government, I don't know why I just forgot, large cap company, sorry, government, and SMEs and startups, right? And I left off government because government plays a part in all three of these. Large cap companies, large market cap like Google, the IBMs, and so on out there in the world. They, of course, many of them have well-known quantum computing efforts that are really world-leading and so on. SMEs like Xanadu are playing a huge role since, how long since D-Wave first launched? It must be 25 years, right? 25 years since the world's first quantum computing startup. And I think we're getting more and more familiar with kind of these three legs of this world, right? And there's pros and cons with all of these models. And I've listed some things here that just to make you read, but of course you can think of your own pros and cons. The first point I would argue about for-profit, large cap, and SMEs is that short-term incentives, or venture scale, or venture timeframes, or whatever you want to call it, very much influence the technical design of the machine. And we can argue about that. Maybe you don't agree with me. But think about the hardware that's become available out there in the world and ask whether or not it's been influenced by what can provide a return or the fastest return on some people's investment into the for-profit. And then you can step back and say, if I didn't have to worry about that time scale, is this the hardware that I would build? Or is this the quantum computer design that I would build? And in many cases, the answer might be yes, and then that's a pro. You have stepping stones on your roadmap to building something like a fault-tolerant machine. But even a fault-tolerant machine, what's the biggest incentive to build a true fault-tolerant quantum computer? Shor's algorithm? What's Shor's algorithm going to do for us? Break 2048-bit RSA encryption? That's the goal, right? Is that a... What's that?
Make more money for the companies?
I wasn't going to say that. We're being recorded, right? So. No, but if you follow that chain of incentives, right? It's very much tied to I think this idea of industrial internet type encryption and so on. So does this for-profit model lock in the best design choices? Hardware and control stacks are proprietary. You got to have my colleague Francesco Bova here to argue the pros of proprietary hardware and software. There's certainly, a well-established literature in the economic fields about why there's pros. Of course, you get the protected trade secrets, you have patents, and all this type of stuff. But one thing I would argue, especially to this group here, is point 3, is that the culture of proprietary quantum computer design, causes frictions between us. How many times have you walked into a quantum computing effort and been asked to sign an NDA, and then you can't go home and tell your friends, right? I just want to tell you guys what I saw, but you're not allowed to, right? So in some sense, that's a pro. In some sense, that could be a friction. We'd all like to collaborate like we did when we were academics to move the field forward. And also, I mean, I don't care. But if the government wants to come in and regulate my quantum computer, how are they going to do that without visibility into the stack? Okay, so if you didn't like that comment? Okay, so, and the reason I mention this is because of that. AI sort of did take off at such an exponential pace that it got way ahead of regulators regulation is way too late. Maybe we could argue that point. But if quantum computing is going to really revolutionize the way we do calculations, the siloing of proprietary hardware and software will certainly affect that. So are there other models? And you can guess there are, because that's what I've been talking about. So another model for scaling, again, writ large, scaling in terms of every aspect of what we do with quantum computing could be an open source foundation. And it's a great audience here to think about open source projects, because many of you, or probably most of you, work on open source projects. But a foundation is just really a way of organizing open source projects. So a typical open source foundation, it could be a for-profit, but it's often a nonprofit, and it's a membership-based model. So we have a nonprofit where members buy in to basically see the development of the stack and to participate in the development of the stack and to build a community that surrounds that effort. And there's all sorts of different technical projects out there. There's thousands and thousands of projects under just the Linux Foundation alone. Who hasn't heard of Linux? No, just kidding. Don't put your hand up. So of course, the most famous open source model, Linux, and the foundation around it, the Linux Foundation, was just sort of an umbrella for many types of projects. In a large sense, was our inspiration for open quantum design. And I'll talk a lot more about that model. Who uses PyTorch? Who developed PyTorch originally? Meta. Right, it was Meta, right? Meta developed PyTorch, and it was opened, and we all started using it. And at some point, I could think Meta says, why am I paying for an open source software suite that the entire world uses when I should be able to get other people to contribute? PyTorch has now been moved into a foundation, a literal Linux Foundation type model. And so if you Google PyTorch Foundation and you look at the members who are contributing to the development of PyTorch aren't just Meta anymore. It's Meta, it's NVIDIA, it's Microsoft. It's players that you would typically think would be competing, now all play nicely together under one of these Linux Foundation charters. So it's a very large project, and it's very well managed, and it's essentially a nonprofit open source foundation. RISC-V is the other one I just wanted to mention. Who's heard of RISC-V? Okay, great. That's great. So what is RISC-V? It's an open source, basically, instruction set architecture. Okay, it's exactly under the Linux Foundation model. It's a member of the Linux Foundation, but it's it's an open source hardware design. And so what does that mean? So I'll show you our open source hardware designs, and essentially RISC-V is one of our inspirations. So it's a chipset architecture. It's a list of standards that are developed by an open source community in this nonprofit organization. You can imagine it competes with other proprietary architectures like ARM, right? AMD, Intel. This is the open source alternative. RISC-V is a nonprofit. It doesn't actually build the chips. It just publishes the designs and the tool chains and the specs and so on. And for-profit companies come in and build RISC-V chips. You can get a RISC-V laptop built in China fairly easily. So it's really an open source design in some sense that I think is a very compelling model. It's interesting because people say, RISC-V, it's not popular because it's the best chipset architecture. It's just popular because it's the only open source one. But okay, so technical design considerations aside, it's a very thriving sort of community. I'm here today to announce, essentially, the launch of Open Quantum Design, which we've been working on for a few years now. So this is our open source, if you want to call it, instruction set architecture, design, standards for an ion-trapped quantum computer that I'm going to tell you a lot more about. This picture on your right are the blades of a blade trap quantum computer built to suspend this ytterbium ion 171, this isotope, in midair, essentially in the vacuum off the tip of those blades, and I'll show you a lot more about it. Me, Who are the people involved? Crystal Sanko, Rajabul Islam. If you don't know them, they were Chris Monroe's students in Maryland, did their PhDs doing ion traps there, went to Harvard and MIT for postdocs in Misha Lukin and Marcus Greiner's group, developed a huge amount of technology that was transferred out of those labs at Harvard and MIT into the groups in University of Waterloo at IQC, have integrated all sorts of designs between these experiments and these amazing academic groups into this ytterbium blade trap quantum computer that we're going to talk about. Greg Dick is our CEO. You may remember him from such organizations as the Perimeter Institute for Theoretical Physics, where he was an executive director for many years. So Greg is an expert in establishing and managing essentially very large nonprofit organizations. These are the ions. We literally have working quantum computers in the basement of Institute for Quantum Computing that are trapping ions and performing all sorts of operations on them and so on. The current generation, version 0.1 or whatever we want to call it, of this design, basically traps about 12 qubits and can manipulate them and so on. Ion traps, I can talk for ages about all the interesting intricacies of how ion trap quantum computers work, but they're a very exquisite control problem. Actually, if you look at the blades and you look at the vacuum chamber, these are very large objects. If you look at the trapped, why are they ions? You strip off an electron, and so you can control the resulting ion with an electromagnetic field that is generated by those blades. I'll show you more pictures. It's just very much an exquisite control problem to take those ions floating in real space and turn them into qubits and to manipulate them with qubit processes and so on. So the new design that we're releasing open source should, in theory, be able to trap and address something on the order of 50 qubits. I just wanted to show the ytterbium 171 energy level diagrams for all the AMO physicists out there. I don't know. Literally, why am I showing this? It's to show you how difficult of an AMO problem this is. These are all the energy levels that could be addressed by all sorts of different lasers. And every ion, every atom, in these neutral or ionic systems has different, basically different energy levels. Why does that matter? It matters for many points of the design. In this case, the qubit, might be between those 0 and 1 levels at the bottom. But there's all sorts of complicated processes that go into the design of these AMO machines around cooling. So these things are cooled, in the trap using lasers in a vacuum chamber that sits at room temperature. So to get back to that point about whether or not you need cryostats and so on, these are room temperature devices that use laser cooling and trapping, essentially, to get your, what's the hard part about scaling a quantum computer? You have to build n qubits that are completely isolated from the universe in all respects, except when you want to address them with pulses, and then they have to be perfectly addressed with just exactly the right laser pulse in this case, in order to prepare the state or to do a readout. So this gives you an idea of the control problem in some sense that that goes into all the work. And Gilbert and Sai are PhD students who have now graduated from University of Waterloo. And one of the things we're trying to do with Open Quantum Design is to keep this amazing talent who's built these devices, here with us in Canada. A couple points about the energy level diagram, which is interesting in terms of scaling, is that these ytterbium atoms they use qubit addressing through an ultraviolet laser. You could say, who gives a shit? It's just another laser. I got to see these lasers all day when I'm in the lab. But these, the exact line frequencies in the lasers that are used to address these things have to be available from industrial vendors. So the highest power laser that we can buy happens to be an ultraviolet laser that's used in the semiconductor industry. And so like all quantum computing efforts, we have to lean on industry, on conventional industry, in order to give us the parts that allow us to scale these things up. So these design choices go in right at the level of the atomic species, essentially, that we're building into these quantum computers. The blade traps are mounted. And why do I keep showing you these pictures? Number one, I don't have enough slides. Number two, you will rarely see the actual working, bare metal device a for-profit proprietary quantum computing stack. And what we're doing in Open Quantum Design is showing every aspect of the bare metal, all the design specifications for how to build them, and the tool chains and so on required for things like alignment and preparation and so on. So that's this blade trap, looking at it along another axis. It's about, I should have brought it. It's on my desk. It's about this big, that sample holder, that blade holder. Again, the reason that we've chosen this design is because it allows for exquisite optical addressing. So lasers can be shone in upon multiple axes to do all sorts of processes related to this crazy energy level diagram there. The blade trap is mounted in a vacuum chamber. Once it's closed up, it's sealed in there forever. So the experimental team is in the process of mounting this blade trap into this vacuum chamber, which I'll show you more of. Once it's mounted in there, they bake it in an oven at 900 degrees up at the University of Waterloo's clean rooms in Rack 2. Someone's got to be standing there watching that oven 24/7 so it doesn't light the whole facility on fire. But the reason that is done is that because, again, these are room temperature devices, and there's a huge amount of outgassing from the chamber, from the blade trap ceramics, from all the metal and wires and everything inside there. So these things have to be baked in an oven to get all the gases out. Then they're sealed up. They're pumped down into vacuum, one stage of vacuum. I can't remember exactly the specs. And then an ion pump is put on them to get them down to something like 10 to the minus 13 torr. What happens is Rajabal then takes the vacuum chamber, puts it in the trunk of his car, and drives it somewhere across campus to put on the optical table, and he hopes that the vacuum doesn't break. But once these things are sealed up, they never become unsealed. Ions are sprayed in there. I don't think I have a picture of the ion source. And they're caught in the electromagnetic fields of the trap. The lasers turn them into qubits. And then after a while, they're released from the trap. They drift towards the walls of the chamber, and they get caught in an ion pump and pumped out. So these things are under a more pure vacuum than you find in basically outer space. Here's one last picture of the vacuum chamber. It's not like I'm obsessed with the vacuum chamber. But it takes a lot of work to put together. There's a lot of processes that have to, the experimental groups have to strictly adhere to in order to make sure that this thing works properly. All of those those processes, the tool chains, the designs, those things are all open sourced, right down from the CAD designs for the vacuum chamber. So if you want to build an open source quantum computer under this design, you merely log onto our GitHub and download the CAD designs, go out to a vendor, get them machined up yourself, put them under vacuum, build your blade trap, you're off to the races. The reason I'm showing you this is, again, because this is all open sourced. Everything here is right from the bolts to the machining specs are being released. If you look on the right-hand side, you basically see the ions are in the middle of that trap inside the vacuum there. You can see all sorts of other, basically optical access and so on into the vacuum chamber. Okay, so that's a bunch of pictures. Why are we doing this? Why open source? Why would we take all of this valuable intellectual property and basically just give it out to the world for free? So, you probably have your own ideas for why you like open source projects. First off, number one, research and development takes place in a large community of members. Okay, that's us. Everyone who wants to be part of this quantum computing hardware, software, control stack, can come and contribute. And there's certain, let's say, guardrails put in place, as you can imagine. Who accepts the PRs, and so on. But this is all set up under a charter. So typical Linux Foundation open source efforts have what they call a charter, which is the expectation that members are given to how they kind of operate in the space. I think a lot of us in the industry already understand the concept of open source, and lots of us, especially many here at Xanadu, are open source advocates. So again, I'm preaching to the choir in many cases here, but I think it's just important to recognize that there are open source communities for us, QOSF, Unitary Fund, many of these run open source software projects. What we're trying to do is give the community a piece of hardware that's open source that we can sort of coalesce our efforts around, okay? So it's a combination of, not just software projects and control projects, but the actual hardware to focus on. I'm going to talk more about this, but for-profit members are certainly welcome into open source communities, and PyTorch is the typical example, where it's essentially run by for-profit large cap members who all get together and play nicely in the open source sandbox. The reason we chose an open source foundation under this Linux model is because it's a proven mechanism for collaboration. We know that people can play fair in these open source sandboxes. An open development community is a great way to attract people, keep people, retain people, develop a community in the region, and also, I don't want to say crowdsource, but in some sense, outsource some of the problems and some of the testing, as maybe the beta testing on some of these devices. Who said it? Given enough eyeballs, all bugs are shallow. I'll let you think about that. Is there a clock in here? 10:05. Okay, I just want to stay on time here. Okay. I think Torvald said that. I might be wrong. I don't know. The open source quantum computing, the computer that we're building, and all of its designs, can be used by anyone who wants to learn how a quantum computer works. Okay, so that includes universities, any organization that wants to learn about the basics of designs, and we have educational and outreach programs that will train the next generation of scientists. Designs are developed by a community in a transparent way. So members who log into the GitHub, and I'll show you the GitHub, get to participate in the designs, and then those designs, those code bases are open sourced. But what is also open source is the development of the APIs that let you log into the device. So yes, you'll have a cloud service at the top of this device that we're building where you can log in and specify your circuit that you want to run in principle. But if you're a little bit more of a, say, AMO aficionado, we're also releasing APIs at the lowest possible level of the stack, and actually several places in between, where you can log in and even do things like pulse shaping and so on. So if you wanted to experiment with different types of native gates or things like that, these APIs that are being developed open source will allow you to do that. So I think there's lots of reasons to think about this open stack. This is, well, okay, up until Wednesday, this is what our stack essentially looked like. So on the left-hand side, we have different interfaces. We call them digital, analog, and atomic. Digital is maybe the one that you're used to if you're used to circuits. You want to make a circuit to do quantum phase estimation or something like that. Analog is like a pulse level control where you would imagine that you have a Hamiltonian that you turn on and off for certain amounts of time. Okay, so that's kind of our distinction between digital and analog. And atomic, again, is if you really want to get into the nitty-gritty and see the difference between terbium and barium ions or something like that in the traps. Under development now by a great team of people, including my students on the right-hand side there, are the intermediate representations. Okay, so right now, the digital layer compiles down to OpenChasm. I'm sure a lot of you use OpenChasm. And the analog and atomic layers actually take, we have custom sort of intermediate representations. One's called QSIM, one's called OpenAPL, developed by Yihong Tao. And these are sort of the lower level IRs that you would need to run the quantum computer. On the right-hand side, we have our classical simulation or emulation backends, including many that you're familiar with. PennyLane, I never heard of it. Yao, famous for all of its performance, benchmarks, maybe famous by Roger here, and so on. We have an IonSim Julia backend that's specifically like the kind of hardware simulator. What we're also doing is building the compilers in an open source way down to the FPGA modules and eventually into those bare metal trapped ion devices that I showed you the ytterbium version of. That is a very interesting problem. So if none of you have ever programmed FPGAs or thought about how you connect the FPGA control of your quantum computer, say, to PennyLane at the top, that is an incredibly interesting compilation problem. And so we're going through that exercise right now. And I encourage anyone who is serious about developing quantum computers to get on board and start looking at this. This is the FPGA control. This is called a Duke Arctic Extension, DAX Arctic Module, which is developed open source by the trapped ion experts at the Duke Quantum Center. So it's in itself an interesting open source microcosm within the larger open source project. So it's an open source FPGA system that can be used to control atoms, but there's a for-profit company called M Labs that you can purchase one of these configured FPGA modules from. So yes, it's open source, and if you wanted to, you could build your own, but you have a for-profit company that comes in and will sell you a prefabbed version if you don't have the time, and nobody ever has the time. So I want to get back to that model because I think it's important in terms of for-profits orbiting around these nonprofits. So we have a couple great FPGA programmers in the group right now that are interfacing all the way up the stack. I'm going to blast through some of these features because this is all open source. You'll be able to see this soon enough. Our cloud-based, the APIs and so on that allow us to will allow you to access the machine through the cloud are developed. We have servers already that we're using to test out these APIs on. We have different types of compilation problems. If I go back a couple layers, it might be too small here to see, but there's at least 3 interesting compilers that we have to build that bring us down from either the digital to analog layers, into that FPGA control. And so thanks to Roger here and Semimol and other people, we've been working on all sorts of, I hope, modern implementations, including visitor patterns, which I just learned about on Tuesday, for these compile steps. So if anyone is a compiler aficionado out there, get on board and help us out with these compilers. Everyone's favorite thing, documentation. I don't know. We'll do that last. No, just kidding. Final thing, I am a theorist. I work at a fairly high level of the stack, let me put it that way. I'm a huge believer in the fact that the hardware that we develop at the bottom of the stack is still in a position where it influences our design choices at the top. So this goes a little bit against what we think in terms of hardware agnostic offerings out there. But of course, maybe many of these things could be handled in a compiler. But let me just give you one example. Here's Gilbert and Rajabul's design for it doesn't matter. A bunch of lasers coming in and doing the qubit manipulation inside the vacuum chamber there. One component of this stack which is special, and again, the reason I can tell you without a bunch of NDAs is because this is an open source design, is the digital micromirror device. A DMD device is found in projectors. Where's your projector? I don't even know what's going on here. Oh, it's down there. Yeah, so, okay. I'm not sure about that one, but wow. Yeah, so oftentimes projectors, there's 2 different types of projectors, but lots of times projectors work with a digital micromirror device where every pixel of that projector is a tiny little mirror which moves in order to address RGB or something like that. So, depending on the resolution of the device and the basically timescales and so on, this digital micromirror, which is an industrial fabricated object, I mean, you buy these things from like Texas Instruments and other places, can also be used to not address pixels on the screen, but to address individual qubits in this device. When Rajabul was at Harvard, he implemented this DMD device into one of the atomic gas microscope experiments there, and then translated that up into our design at the University of Waterloo. So this is a very special part of our stack, and the reason I'm mentioning it is one thing it does better than any other design is mid-circuit measurements with essentially 0 crosstalk. So if you think of your quantum circuit and you think of unitary gates, but then if you wanted to perform a measurement of a single qubit somewhere in that circuit, not at the end to read the state out, somewhere in the middle, that's a very difficult problem. Many hardware designs right now either address that thing with a beam, but that beam has a profile, that laser beam has a profile, which can basically crosstalk the physically adjacent qubits. So it's very hard to narrow down those beams enough to basically give you, individual addressing at that level. So hardware vendors will shuttle out the ions or the atoms by physically moving them, address them with a global beam, and put them back, which slows everything down to an incredible amount. What the DMD does is allow you to do almost perfect zero or very small crosstalk mid-circuit measurements without that shuttling. So very fast, very rapid. The reason I told you all this boring details is this really would influence the circuit design. So for example, if I want to build a circuit with mid-circuit measurements that operates at a certain frequency, this kind of nitty-gritty detail really matters. If I know about the hardware, I can design the best circuit up at the top of the stack. So I'm a big advocate for hardware matters. How do you make the best quantum computer, and how do you make the best control system and design the best algorithms? It's knowing details like this, everything of which will be open sourced. I'm not pitching the members here, but you're probably asking yourself, why would anyone join? This sounds terrible. And again, the members of an open source foundation are very much coming from different walks of life, academia, industry, and so on. And one common thing everybody gets is access to the design forums. So if you become a member, or if your organization becomes a member, you're on the GitHub, you're on the Slack, you're looking at the designs, and you're issuing your own PRs. So if there's something that you as an organization would like to see this quantum computer do, maybe you want to do Shor's algorithm in 2 years on 2048-bit RSA, or maybe you want to turn this thing into an optimization play or something like that. You get in the design forums and you start influencing the designs with your own scientific or philosophical priorities. So that's a big incentive for everyone to get involved in these things. There's opportunity to be part of the definition of abstractions and standards and so on. There's lots of standards being tossed around out there. There's abstraction layers that we're thinking about to make the top of the stack agnostic from the bottom of the stack and so on. I argue that those are probably best designed in an open source environment. Benchmarks, quantum volume. What's the quantum volume of a device? What's the best quantum volume measure? We will provide open source benchmarks for other organizations to use on their own hardware. Education and outreach. I spend all my time teaching. I don't want to talk about that. But no, seriously, it's you bring a large, diverse community in, including many academic groups, especially smaller universities that maybe don't have their own institute for quantum computing, right? We can really democratize, in some sense, access, which is my last point, across the entire open source ecosystem. Unlike Xanadu, we let our software people in the lab. No, just kidding. Is Josh here? I don't know where he went. Here's Josh and Roman on Wednesday looking at, and there's me, they even let me in the lab, looking at the ion trap quantum computer and poking around in there. I think that's incredible. There's all sorts of amazing things going on in the lab that even I think software people can appreciate. So for example, one thing we're doing is building a very modular piece of optics here. So we're not just building an academic machine that has optical table where you buy lenses and you bolt them onto the table. What Rajabal's team is doing with a pretty large amount of engineers at the University of Waterloo is designing compact three-dimensional modular optical designs. And you can see on the right-hand side some CAD drawings of an eventual, this is the machine. This is basically all the control optics and computers built around the quantum computer. That CAD design and everything that goes into that construction is open sourced. Now I know what you're thinking. When you're programming open source, you're programming communism. No. This is the slide I spent the most amount of time on, so I'm leaving it up here. Oh, what am I going to get censored on? We're totally not anti-capitalist. We're not anti-capitalist, okay? Open source and capitalism are not mutually exclusive. Where did Sean go? I guess he left before that, but with the right licensing, these two communities can play together, okay? Apache 2.0 is a great example, right? We can open source these designs under Apache, and for-profits can build the hardware. That's the RISC-V model. It's a proven model. There's tons of RISC-V computers. Companies can, if they're building their own devices, adopt some designs that we like. The DMD, for example, where it's open sourced. If you see the digital micromirror and you have your own ion trap, here is the open source design. So we can improve proprietary hardware. The Open Source Foundation provides an ecosystem for small startups like somebody who knows how to build that trap, how to machine it, how to attach the blades, how to align them, and just like that MLabs thing I told you about. Yes, you open source designs, and people can build those designs, but maybe they don't have a clean room, or maybe they hate machining or whatever it is. Smaller, I call them component companies, but somebody told me that's the wrong word. But smaller component companies can build these things and ship them out. And that's one of the ecosystems we're trying to build around Waterloo and Canada around this device, is some of these sort of component companies that who use the expertise on campus and off to build their own startups and launch their startups. Again, licenses like Apache allow for-profits to build on top. So this is common in software. Roger, how many for-profits use YAO? 10? I heard 10. So Roger developed an open source simulator called YAO, written in Julia. It's under Apache, right? It's under Apache 2.0? Right. So I'm just going to say some names. Companies like Blue Qubit and other software providers can use YAO as their simulation engine while providing, let's just say either enterprise services, if you want to call it something like that, or the platform to run these things on. So it's the same story. And proprietary hardware companies can contribute to standards. So if Xanadu has a standard that they want to develop, they can come in as a member and do this open source. I'm going to wind down here a little bit. Just want to show you the repo so that you believe me, it's actually there. Everything's private until we launch and we start open sourcing things. But if you're interested to become a member, we're happy to show you the repository. Quantum Ion is the name of the full stack that we're currently working on, but that name is subject to deliberation by the members. So if you have a cool name for our quantum computer, contact us and think about it. All of our intermediate representations are on here. Things that you probably don't care about, like how the CCD cameras detect the ions, the back-end simulation package, certain beam control things, which probably nobody will ever touch. They're all open sourced on this repository. I wanted to end by just blasting through kind of a few interesting philosophies I think we can take away from a combination of open source design and something I know many people here are interested in, and that's machine learning. And so I'm a machine learning advocate, certainly. I work a lot on machine learning with my students. They've taught me everything I know. I see machine learning as, at this stage of the game, being something that we incorporate into the stack, okay? And I'm talking about not about quantum machine learning in the sense that we have an algorithm that we want to run and the hardware speeds it up. I'm talking about machine learning as a way of designing and controlling the quantum computer. And machine learning has a place in many places of the stack, right from the bottom, physical layers, like I've been talking a lot about hardware, pulse control and so on. I haven't talked about error correction that much, but up in that logical layer, we're seeing more and more these days machine learning used for error correction and so on. So I just want to give you a couple examples and talk to you about how this fits into, I think, the broader view of what we're doing with open quantum design and the foundation. So for example, here is a picture of some lasers addressing some ions. This is a paper I worked on with Yi Hong, Rajabal, and Marina Dragala a few years ago. There's a really interesting control problem. Sorry, I just cut and paste all the text there. You don't have to read it. There's a really interesting control problem in quantum computers, which lots of people think is a showstopper. Why don't we have 10,000 trapped ion qubits right now? This equation is the reason. This equation tells me how to take all the laser frequencies and intensities on the right-hand side, that's the omegas and the mu's, and translate them into a JIJ, which is a interaction parameter. So if I want to make a square lattice or a Kagame lattice, XY model, basically you have to solve this equation. This equation is a famous example of what we call an inverse problem. So on the right-hand side, if I have the omegas and the mu's, I can easily take those sums to get a JIJ. But what if I want to engineer things the opposite way? What if I want to make a one-dimensional circuit, or a two-dimensional square lattice, or a triangular interacting graph? That inverse problem is ill-posed. a famous word invented by Hadamard, if you dig into it. So these ill-posed inverse problems are part of the control problems of ion-trap quantum computers. And one of the big breakthroughs we've been able to think about recently is how to approach these from a data-driven perspective. So what we do in the ion trap simulator is run a whole bunch of forward problems and collect data. What are the omegas? What are the mu's? What are the JIJs that result from that? Train a big neural network, which people make neural networks for inverse problems in math, and then solve the inverse problem basically through that neural network, which gives you a JIJ, gives you the omegas and laser parameters, which you can essentially tweak at the end. So it's just an example of the lowest level of ion control now in these quantum computers is being manipulated by very large kind of machine learning strategies. I was going to talk about data acquisition, but I'm going to skip through this. I just wanted to show a picture of me and Raj in the lab, just to, again, brag that they let us in there. This is at QERA. I'm probably not supposed to show this, but I didn't sign the NDA. Sorry, Raj. But in terms of data acquisition at the top of the stack, that's a very interesting machine learning problem too. And my student Severin is working full-time on basically using a neural network architecture that you see on the left there to take the actual CCD camera readout of the trapped ion quantum computer on the right and classify the quantum state with it. So this is, again, an important problem in scale. It's easy to detect the quantum states of 4 qubits coming out of these ion trap or these neutral atom machines, but how do you do 10,000 or 100,000 or something like that? My argument is that you really need scalable control architectures, and I think our best, most modern ideas for scale come from a lot of machine learning infrastructure that's been built over the last few years. If you wonder why it's such a hard problem, on the bottom right there, those are individual snapshots of qubit states. And you're trying to detect the difference between brights and darks in those pixels. And I encourage you to stare at that for a while. And it's very difficult to see the difference between a bright and a dark. So it's a classic machine learning problem, something that's difficult for humans in this case, which we can actually scale using basically like a CNN or something like that, like a classic computer vision architecture. Computer vision is in CNNs and feed-forward neural networks. So these are all part of the quantum computing stack. Language models are increasingly becoming part of the stack. So a very simple way of imagining using a language model would be using something like a recurrent neural network to predict the time dependence of the qubit. So here's a single ytterbium undergoing its Rabi oscillations. And as you can see, there's basically a decay in those oscillations, and that envelope is related to the coherence time. That's basically when your qubit becomes decohered, everything is decaying out to 0.5 or something like that. That's the 0, element of the matrix element, of the density matrix, sorry. On the left-hand side is training data. We take a bunch of training data and we push it into a machine learning architecture, just an RNN, and then we can unroll that RNN as a function of time. And it's hard to see, but the machine learning or the RNN prediction is basically matching exactly the real-time evolution that we can measure for this device. Why is that important? If you can make predictions on the output or the outcome of this type of oscillation, you can do qubit readout with a lot less data and a lot less time. So effectively, these types of prediction algorithms that you build from things like RNNs increase the clock speed of your machine. Right? So the lower you bake these things into the stack, the faster your quantum computer, in this case, state readout will be. And so I think there's all sorts of opportunities for optimization all throughout the stack. I'm not even going to talk about this. This is a teaser. We got to publish this paper, guys. You can take this idea of language models all the way up into LLMs. And here's something we've done, not for the trapped ions, but for the neutral atom quantum computers, where we've adopted a GPT-like language model. On the left-hand side's the encoder, on the right-hand side's the decoder. Into the encoder goes a parameterized, in this case Hamiltonian, but you could imagine a parameterized circuit or something like that. Out the top of the decoder comes the conditional distributions of the autoregressive chain, if you will, which is literally the wave function. We've trained this thing on data. So we've trained this thing on a whole bunch of data at those red arrows. And the blue points are where we've done, I guess, I don't know if you call it inference, but where the model has generalized to calculate the energy in different regimes of this Rydberg Hamiltonian. So we know that these GPT-type models are very scalable and are very good wave function approximators. And this gets back into, open design, open data access, open models, right? I believe the future of a lot of the hardware we're building is digital twins. So we can build hardware, collect data, keep that data, offer it open to everyone else out there, train models off it. In some sense, those models are compression algorithms. We've compressed a huge amount of projective measurement data that we've gotten off these devices into an LLM or into some sort of architecture like that we can then query. How does the quantum computer behave in this other regime? Or what would happen if I calculated this estimator off of my hardware or so on? So as we build out open quantum design and as we start to collect data off of the device, we're going to be building open source data sets. And we've been talking to PennyLane about hosting some of them through PennyLane and Xanadu. And with those data sets, anyone will be able to train these types of generative models and to basically explore the outcome or the output of the quantum computer. And I see it as two kind of routes. On the left is my quantum computer. In the middle there is data flowing into all sorts of model constructions. We can, leverage the data by, again, it's a bias variance trade-off on the upper branch there in order to improve our characterization and control of the device. And we can explore different configurations of the device on the bottom branch by tweaking parameters, just like I did here when I tweaked that delta on the x-axis. I can tweak parameters to different regimes of the operation of the device to see how it'll behave. Once we do that, we get our second iteration of design, hopefully with more qubits is the idea, is you're scaling up the number of qubits and the number of gates. Repeat, collect the data, build the models, do the co-design. All of this will be open sourced. So I'm going to leave it at that. We don't have a lot of swag yet, but we do have maple syrup because it's a full stack. So I encourage you guys, anyone who comes by Waterloo, swing by the OQD office. We have great teams in the laboratories. We have great theorists. We have great, engineers, control stack design. But we need more. So if you're interested in what I've been talking about, if you want to become part of Open Quantum Design, here's the website. I look forward to speaking to all of you. And thanks for your attention.
All right, yeah, round of applause for Roger. Okay, we'll get to some questions in person here. We got mics to be handed around, so raise your hand and we'll get to you.
So you mentioned using machine learning for some of the measurement procedures. Would the idea be to actually implement the ML model directly at the FPGA level, or would you collect the data and process it sort of offsite? I mean, if it was closer to the metal, obviously, I guess that would allow for like mid-circuit measurements.
Right. We have a very interesting collaboration with teams at Sherbrooke who are building memristor arrays. And so one thing you can do with these memristor arrays is basically bake in certain types of architectures right in kind of the FPGA level. So one dream would be to design neural network architectures, actually not very large ones. These are typically small ones, but some of these, I guess, readout and control problems can be baked down into small pieces. And then to program those FPGAs once, and then basically have that machine learning part or that neural network part be right in the vacuum chamber, or as close to the vacuum chamber as possible here. So yes, I think that's a huge aspiration that we have. Right now, I get the data through email. So it's not quite the same, but yeah, that's the aspiration.
Thank you.
Are ions the only thing that you have right now, or are you also publishing or planning to publish things with superconductive qubits and so on?
So I got excited there. So I'm very much believe we have to focus around a piece of hardware at the start. And one of the reasons is we don't have a great abstraction layer in the stack. Like I don't know how to go from superconducting qubits right now to some of the compilers that we have that we're building. The second type of architecture I would like to target would be the neutral atom Rydberg devices. So they're different in many ways. They have, they basically use optical tweezers instead of, to grab each individual atom. It's a neutral atom. But that type of optical addressing is possible in this architecture that we're building, and Crystal and Rajab will have experience from their time at Harvard, MIT in these groups. So I'd say the second hardware that we'll build at the bottom of the stack will likely be a neutral atom device, and then we'll expand outwards from there. So eventually, would like to have open designs for every competing architecture at the hardware level, but it's going to be ions first, then neutral atoms, and then we'll see.
Hello. Naive question. Why not photonics? Why not photonics?
No reason you can't have photonics integrated in here. I would argue the way that photonics would fit would probably be for the atom, so the atom arrays or the, whatever we're building, to do the entanglement part. So you can imagine that the ions or the atoms produce like true entanglement in a register that can then be read out. When the photons come out, those come out entangled. Those can go into a photonic circuit, and you can have all your error correction and so on in that circuit. So there's no reason why not. In fact, I think it's a great idea to integrate photonics.
My question is, say I have a team of laborious graduate students, and I want to build one of these. Realistically, how much is it going to cost me, and what sort of time frame would you expect?
Bill of materials is about 2.5 million. That's it. And then time. What is your grad student's expertise? I mean, one thing you have to think about is whether you can design, align the trap, and align it in the chamber, break the chamber, and these types of things. So it might make sense that that's outsourced to someone like our team who could sell you that piece, but that just makes it cheaper, I think, if you want to do it all yourself. So the bill of materials for us is about 2.5. What I want to do is, that's in a special lab. You can buy essentially boxes that are humidity, ions are sensitive to humidity for some reason, and air pressure and things like that. So you can basically buy prefab boxes now that sit around your optical table for about $500,000. So bump that up to $3 million, and you have an open source ion trap quantum computer that you could put anywhere. You can put in the lobby of the CIBC building here or something like that.
Are there any supply chain issues if you're not in academia or government? In that bill of materials, are there any supply chain issues if you're not in academia or government? So
there's no ITAR type. There's nothing everything here there's chip traps for ions that are covered under ITAR, like you can't ship them to certain countries, but nothing like that.
Okay, it's not like some of the laser things where there's certain strains of lasers that are hard to get if you're not kind of an industrial
Lasers
player.
have a lead time. I mean, I don't want to complain, but the amount of time I got to talk about lasers with these guys drives me nuts. But yeah, there's definitely lead time on some of these lasers that you would have to think about. But they're all commercially available. And again, in particular, the reason that a terbium was chosen was because there's an industrial option for the main laser, which is in the ultraviolet, that can be procured relatively easily. Yeah.
Any more questions in person? Right, one there.
Yeah, thanks for your talk. I was just curious if you are aware of Sonara, the open hardware ecosystem. It's like a control stacks for ion trap quantum computing that works with the Arctic software ecosystem.
Yep.
Yeah,
Absolutely.
and okay, well maybe they're like a good candidate for membership.
We encourage the vendors to be members. So that in some sense, I don't know if they're vendors, but I actually think some of the team has written drivers for some of these things. So this kind of collaboration is exactly what we want. Absolutely. Thanks for that.
All right, any more questions in person? I have one, actually. Maybe I can go.
Yeesh.
So you mentioned it a little bit, like there was a slide you had on licensing and stuff like that. I think for software, it's relatively easy, right? You just copy and paste some comment at the top of every code block or code file, and you're pretty much done. But when you start to get in the world of physical things, copywriting and patenting becomes a really big issue. So what are you doing here to not piss off anybody else in this industry that has a patented design on an ion trap or something? How does this work?
Yeah, it's a good question. It does get more sticky when you get down to the hardware level, for sure. Some of those licensing arrangements, so one thing is we have an advisor from RISC-V, Zvonimir Bandic, who was one of the founders of RISC-V. And so he is actually a licensing expert, and we may have to think of bespoke licenses down that part of the stack. I'm not sure everything can be open under Apache. Like a CAD design, right, it doesn't involve code or something. It's a little bit more tricky. So that's one of our biggest challenges, I think, is to understand the licensing around specifically these hardware people. In terms of pissing off companies, I mean, I just don't see it. I mean,
well, yeah, like certainly, like with the like you're not exactly copy pasting the framework of like the Linux and PyTorch foundations, but they're predominantly like software, right? So this is something where you kind of have, this is uncharted territory for sure.
That's why I mentioned RISC-V, because it's an ISA in some sense, but it's also the tool chains for how you build, and they have licensing that would be different from a typical software Linux foundation for sure. I got to say though, one of the impetus or one of the reasons behind launching this openly was, and I won't mention any names, but some of the scientists really found that the for-profits were taking a lot of the community, I guess, publications and community effort out there, which is open on the archive, and then patenting it. I mean, you can imagine, right? Of course, it makes sense for the company. But one of the things that Open Quantum Design does, number one, we own 100% of the intellectual property, because University of Waterloo has an inventor-owned IP policy, right? So we've essentially moved all of the IP out of the University of Waterloo into Open Quantum Design. That allows us to patent things in OQD if we wanted to that were trade secrets before they were open.
Cool. We had one question online here. When will everything be when will all the open source work be launched and available? I think it already is, right? Yeah, I went on your GitHub and most of it's there.
Lots of it's still private.
Okay.
We're looking for a full launch by March this year, where we'll make everything public that's ready to be public and announce all the members and so on. Hint, hint, some of them might be in the room. And so just stay tuned.
Cool. All right, well, that'll do it for this talk. Thanks so much, Roger. That was really interesting. So one more round of applause for Roger.